Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. We are from Group 16 for Presentations Plant Design Project 1. The title of our plant design is Monetizations of Waste Plastic for Chemicals Productions, Alkaline Hydrolysis. We as a team, my name is Marsha binti Muhammad Najib, and my friend Siti Haja binti Azmi, Shasha binti Ong Ahmad, Nur Afika binti Said, and Kwok Ting Shen. We were being supervised by Dr. Nora Fiza Harun. So moving forward to the introduction, we have chosen PET, polyethylene terephthalate, as our chemical feed, where it has the chemical formula of C10H8O4. Why we are choosing the polyethylene terephthalate is basically 4 reasons. The first one is PET is very good as a good heat and also chemical resistance at elevated temperature. Secondly, it has a higher properties where it is not being destructed when it is being applied to a higher temperature. Thirdly is where it is safe and strong material. And last but not least is it is easily to be recycled. So based on these 4 reasons, this is why we chose polyethylene terephthalate as our feedstock. Moving forward, to have a better understanding, let us understand the problem statement. So why do we design this kind of plant design? It is basically due to the high cases or issues regarding plastic waste, where we can see that the only common practices that are being used in Malaysia is basically landfills. But knowing that landfills will affect in 2 major parts. The first one is the place where we need more space, and then thirdly is due to the pollution that is being made by the landfills. So these 2 things, major things, should be taken into considerations. Therefore, we have chosen this plant design and that it will save significant amounts of energy. So the objective of this plant design is to design a profitable chemical plant which monetizes waste plastic using PET as feedstock and for ethylene glycol and also terephthalic acid productions. Therefore, we are using the ethylene as our feedstock, and ethylene glycol and also terephthalic acid will be our major product. The second one is to apply a cost-effective and sustainable process route in the plant. Thirdly is to be able to produce terephthalic acid and also ethylene glycol in a safe manner. And last but not least is to be able to produce a plant design project where it is environmentally friendly method. So these will be our scope of work. We will conduct literature review for the main as the first stage. Then we will conduct a preliminary hazard analysis. We will choose the best process route, and we will develop a complete material and energy balance and proceed with the process flow diagram and complete it with a piping and instrumentations diagram. And we will also provide the hazard study. So as for the literature review, we have found several methods which are hydrolysis, aminolysis, monolysis, methanolysis, glycolysis. As you can see, there are 2 references that we are using as the references, and based on all of the methods and takes into considerations of the product itself, we have chose hydrolysis as our methods, where hydrolysis can be categorized into 3 types of hydrolysis. So therefore, we have chose this alkaline hydrolysis compared to the acidic and also natural hydrolysis. Why do we choose alkaline hydrolysis is because of if we take a look at another perspective, which are the cost efficiency, we've compared between the alkaline hydrolysis and also the acidic and also natural hydrolysis. Alkaline hydrolysis is much more cost effectively, as the alkaline is much more cheaper compared to the acidic and also steam and water. And the annual productions, to conclude the part of market analysis of our product for terephthalic acid, and our contributions of terephthalic acid will be 0.14%. A small amount, but with a significant value that will help to fulfill the demand.
Greetings to our supervisor, Dr. Nur Fidza, and to our internal examiner, Dr. Lam Man Ki. Before I start, allow me to introduce myself. I am Nurif Kavinti Said from Group 16 PDP, and I'm going to present about process screening part. The most economical method to produce terephthalic acid, also known as TPA, and ethylene glycol, also known as EG, from PET is through hydrolysis. Hydrolysis of PET received attention after the discovery of PET synthesis directly through TPA and EG, where the purity of TPA produced are also high. So, hydrolysis of PET can be classified into three types, which include acid hydrolysis, where the feed consists of concentrated sulfuric acid and PET, alkaline hydrolysis, where the feed consists of ammonium hydroxide and PET, as well as neutral hydrolysis, where the feed consists of water and PET. Firstly, I will explain about acid hydrolysis. So, this is the block diagram. It is performed by depolymerization of the PET by the presence of strong acidic solution such as sulfuric, nitric, or phosphoric acid. However, the most frequent acid used is sulfuric acid due to its fast reaction. So, this reaction starts with the addition of concentrated sulfuric acid and PET into the reactor with continuous stirring at temperature around 82 degrees Celsius. The mixture is then added with water where precipitation of TPA will be obtained. In order to remove other contaminants such as dyes, alkaline such as sodium hydroxide is added. Thus, the PET sulfuric acid mixture with water are neutralized and the insoluble precipitate of the dye can be filtered. To purify the TPA, the mixture is added with other acid to convert the sodium terephthalate into crystalline TPA and the precipitate is filtered. In the last step, the remaining mixture is mixed with organic solvents such as trichloroethylene where EG are soluble. The two phases is then distilled to recover the EG and the trichloroethylene to be recycled back to the process. Secondly, I will explain about alkaline hydrolysis. So, this is the block diagram. This type of hydrolysis uses alkalines such as sodium hydroxide, ammonium hydroxide, or potassium hydroxide to depolymerize the PET. A very high purity of TPA are obtained by alkaline hydrolysis with ammonium hydroxide as the alkaline have been studied. So, the reaction is heated up to produce ammonium terephthalic and SEG with some unreacted PET. The mixture is then sent to a crystallizer unit for separation where slurry of ammonium terephthalate is separated and the slurry is further centrifuged and heated in furnace to obtain purified TPA. The EG and ammonium mixture from the crystallizer is sent to the first distillation column for recovery of ammonium hydroxide and are recycled back to the reactor. The bottom product from the first distillation column is then sent to the second distillation column to recover the EG. Thirdly, I will discuss about neutral hydrolysis. So, this is the block diagram. So, firstly, the reactor containing mixture of PET and water are reacted in an elevated temperature and pressure. The reacted mixture will then form a solid portion of TPA and liquid portion of EG after cool down. The EG is then recovered through distillation and the solid TPA is recovered through heating at higher temperature with steam. The heating of the solid TPA is then cooled to temperature below the dew point of TPA and the solid TPA is formed. This method is very environmental friendly because the production does not require any use of unsafe chemicals for the environment and does not produce any harsh byproducts. However, the purity of TPA produced from this method can only be achieved around 70 to 80%. Furthermore, each method in producing TPA and EG from PET has their own benefits and drawbacks as shown in this table. From this comparison, it can be concluded that the best hydrolysis technique used for the plant is alkaline hydrolysis. This is because the process for TPA-EG recovery are simpler as compared to the complex process of acid hydrolysis. The reaction is also undergoing in a moderate temperature and pressure value compared to neutral hydrolysis. Alkaline hydrolysis also could tolerate with highly contaminated post-consumer PET, which is the most suitable for this plant design as the feed PET is from waste.
Assalamualaikum and a very good day to our examiners. So now we are going to proceed with reactor selection and optimization. So in this process, there are two main reactors, which are first the depolymerization reactor and the second one is the TPA solidification reactor. So for reactors, there are two main types, which are first the batch reactor and the second one is continuous reactor. So since the operations needs to meet specific amount of production per year, the plant is conducted in a continuous mode of operation. So now I am going to explain in details on depolymerization reactor. So as mentioned in process screening, the depolymerization reaction is conducted through alkaline hydrolysis. So the reaction involves the introduction of PET and alkaline solution into the reactor, and with enough agitation and heat, the PET will be depolymerized. So the chemical reaction equations of this process is shown on the slide. So in order to optimize the reaction, the best alkaline for the alkaline hydrolysis process is studied. So the table shows the comparison on alkaline alternatives in this process. So the alternatives that we are using is first ammonium hydroxide, second is sodium hydroxide, and the third one is potassium hydroxide. So from the study, the best alkaline for the hydrolysis is ammonium hydroxide. So this is mainly because it has a cheaper cost compared to the others, thus reducing the economical expenses on the raw materials used. Next is choosing the reactor type. So here we have compared two types of reactor, which is first the PFR and the second one is CSTR. So since the process is continuous process, which is why we compared these two reactor, which is both is continuous reactor. So the table shows the comparison for the process reactor of the plant. So from the comparison, CSTR is chosen as the reactor because the reactor provide agitation to the reaction process, which is needed in order to facilitate the depolymerization reaction, which will result in higher efficiency of the reactor. Okay, now moving on, here is the simple reactor block of alkaline hydrolysis of PET with ammonium hydroxide. So the feed is PET and ammonium hydroxide, thus the reaction produce ammonium terephthalate and EG. So here, and then there is the table for the process condition of the depolymerization reactor. So moving on to the second reactor, which is the solidification of TPA reactor. So to obtain solid terephthalic acid, the diammonium terephthalate from the outlet of the centrifuge is sent to a Keene reactor. So this is to remove the liquid contained, thus producing solid terephthalic acid and eliminating the ammonium hydroxide. So in order to optimize the reaction, we study comparison between gas Keene and electric Keene. So for the chemical reaction equation for this process, it is shown on the slide. And then this is the table of comparison between gas Keene and electric Keene. So from the study, we have chosen electric Keene due to more economical in long-term basis, and it has higher thermal efficiency compared to gas Keene. And the Keene is selected to be operated as a plug flow reactor, PFR. So this is the simple reactor block of the solidification of TPA reactor, and where the feed is the diammonium terephthalate and water, and thus producing terephthalic acid in solid form and liquid ammonium hydroxide. So the table shows the process conditions of the reactor. So that's all for reactor selection parts. Thank you.
Now, I will move on with separator selection and optimization. After going through the depolymerization process of PET via alkaline hydrolysis, the product from the reactor will be diammonium terephthalate, water, ethylene glycol, as well as some unreacted PET. Then this liquid mixture will be filtered by using filter in order to remove the contaminating solids, which are the unreacted PET. To obtain the required product, which is terephthalic acid, two types of separators are being compared in order to select the best separator, which include crystallizer and stripper. So, the principle of separation of a crystallizer is the production of crystal, where the differences in solubility is important in separating components present in the melt of the solution by using heat transfer, whereas as for stripper, it involves the transfer of a component from a liquid phase in which it is dissolved to a gas phase by using stripping vapor. For this process, the initial feed should be in liquid, where both of these separation technologies portray the same characteristics of feed phase. However, this process requires solid and vapor phases, where vaporized ammonium hydroxide and ethylene glycol as well as crystallized slurry containing mono and diammonium terephthalate should be the product obtained from this separation process. Hence, the chosen separator is crystallizer. So, this is the block diagram of the process of crystallizer, and the following table are the estimated operating conditions for the crystallizer. Next, in order to obtain the ammonia from the solution, which consists of ammonium hydroxide, EG and water, separation technology should be utilized. Thus, for this process, stripper is chosen. Firstly, the solution of ammonium hydroxide, EG, and water are mixed with lime, which is also known as calcium hydroxide, through a mixing tank. This lime is added with the purpose of increasing the pH values of the solution and making it to be more alkaline, since high pH is essential for effective ammonia stripping. In general, a stripper column is known as a chemical equipment used for physical separation. One or more components are removed from a liquid stream by a vapor stream. Two types of packed column stripper are being compared, which include air stripper and steam stripper, including its advantages and disadvantages as shown in this table. For air stripper, water enters from the top of the column where it is misted over the porous packing material, while air is being blown from the bottom of the column. Most of the volatile organic compounds will be transferred to the vapor phase and removed from the top, whereas treated water will exit through the bottom via countercurrent flows. For steam stripper, liquid feed is fed at the top of the column, whereas the steam input is introduced at the bottom of the column. The liquid flows down the column and through the packing countercurrent to the steam. The packing enriches the stripping by enhancing the contact between the two streams. Generally, stripper is mainly used to remove volatile organic compound, but stripper can also be used for the removal of volatile organic or inorganic contaminants such as organic solvents, hydrocarbons, as well as ammonia. So, in order to separate the ammonium hydroxide from solution, steam stripper is chosen as ammonium hydroxide is very volatile. It is also proven that steam stripper portrays better operability as well as economic performance as compared to the air stripper. Furthermore, the more volatile compounds may be recovered in the top product, which can be reused in order to improve their sustainability. Not only that, steam stripper is also a better option as it can minimize air emissions. So, this is the block diagram of the process of steam stripper, and the following table are the estimated operating conditions for the steam stripper. Lastly, after undergoing through stripping process, the bottom products of the stripper are EG and water. For the recovery of EG, the distillation process is applied by comparing the utilization of one distillation column or two distillation columns. The advantage of using one distillation column is cost efficient, whereas the benefit of using two distillation columns is higher purification. However, the disadvantage of using one distillation column is lower purification as compared to two distillation columns, whereas the disadvantage of using two distillation column is inefficient cost of maintenance. So, one distillation column is chosen in this plant design due to its cost efficient, which automatically reduces the cost of maintenance. In this column, the EG product flows through the column as the bottom product, whereas the water will be vaporized as vapor as the top product. Even though one distillation column will obtain lower purification of products, but it has indeed met the requirement and sufficient enough for the purification of EG when using only one distillation column. Hence, it is preferred to use one distillation column to obtain the sufficient amount of purity of the products, thus reducing the cost of plant operation. Thus, this is the block diagram of the process of distillation column, and the following table are the estimated operating conditions for the distillation column. That's
Hello, hi. So I'll be presenting the mass balance of our process plant. We'll look at the mass balance equipment by equipment. So the first equipment that we will look at is the polymerization reactor. The amount of polyethylene terephthalate introduced to this reactor is 500,000 ton per year, which is also equal to 59,523.81 kilogram per hour. Besides, we also introduce ammonium hydroxide, 3 times the amount of PET, and also water, 10 times the amount of PET as an aqueous medium for the PET to depolymerize in the reactor, which later on will produce the diammonium terephthalate. We have also specified that the conversion yield of the PET for this reaction is 80%. So there will be some amount of unreacted PET that will be filtered out later on from the process. The mass balance of this equipment is performed based on this stoichiometric equation. So from this equation, we can see that we have two reactants, which are polyethylene terephthalate and also ammonium hydroxide. These two reactions will produce diammonium terephthalate and also ethylene glycol. The water introduced in this process is not involved in the reaction, so the amount of water in will also be equal to the outlet, the amount of water in the outlet. So next equipment will be the crystallizer. So the inlet of the crystallizer is coming from the reactor after the unreacted PET is filtered out. So we can see that the inlet of the crystallizer contains 161,205 kg per hour of ammonium hydroxide, 49,609.1 kg hour of diammonium terephthalate. We also have 15,381.6 kg per hour of ethylene glycol, and finally we also have 559,238.1 kg per hour of H2O. So we assume that 95% of the water of the water from the inlet stream will be evaporated, while 5% of the water will exit the stream as slurry. We also assume that 85% of diammonium terephthalate is crystallized, while the rest of the diammonium terephthalate will be in the slurry in the solution. So from the assumption, we can calculate the amount of component in the outlet stream. So after some calculation that have been made, this is the final amount. So the component not exit this stream will evaporated at the above of this crystallizer, which later on will be transferred to the separation unit for further separation. Next is the clean reactor. The solidified diammonium terephthalate and also slurry from the crystallizer will be further burned in this reactor with the help of steam. The mass balance of this process will be performed based on this stoichiometric equation, where the reactants are diammonium terephthalate and also water, which will produce these two products, which are ammonium hydroxide and terephthalic acid. We have specified that the conversion of diammonium terephthalate to terephthalic acid in this process is 70%. So 48,609.10 kg per hour of diammonium terephthalate can produce at least 28,818.57 kilogram per hour of terephthalic acid. Besides, we also find out that from the literature, the H2O steam supplied to this reactor should be twice the amount of TPA produced from the reactor, from this reaction. So in order to produce 28,818.57 kilogram per hour of terephthalic acid, we need at least 57,636 kilogram per hour of steam. So the terephthalic acid produced will be stored in the storage tank, and the other product of the reactor will be returned to the crystallizer to be evaporated to the separation unit for further separation. Next, we will move to the separation unit of our plant, which are the ammonia stripper and also the distillation column. So the inlet of the ammonia stripper is from the evaporated component of the crystallizer. There also have been a few assumptions that have been made in this process, which are the overhead product. The overhead product is 30% of the overall output, while the bottom product is 70% of the overall output. Besides, we also assume that the liquid to gas ratio in this process is 4. So from this assumption, we can calculate the amount of steam that this stripper needed, which are 185,515.6 kg per hour of steam. From this assumption, we can also calculate the amount of overhead product and also the bottom product. Since the main function of this stripper is to strip the ammonia, we assume that the ammonia is fully stripped at the overhead of the product, while the rest of the solution will be coming out at the bottom of the stripper. So the amount of ammonia in the overhead product is 161,205 kg per hour, while the water is 117,068.4 kg per hour, while the bottom product will have 15,381.4 kg per hour of ethylene glycol and also 623,090.2 kg per hour of H2O. Finally, the last equipment of our process plant is the distillation column. So the inlet of this column is coming from the bottom of the stripper. So assumptions that have been made in this process is the distillate product will contain 80% of the overall output, while the bottom product is 20% of the overall output. So the main function of this column is to distillate the lighter product, which is the H2O. So from this assumption, we can calculate that the amount of H2O distillate at the overhead is 519,443.68 kg per hour of H2O, while at the bottom we have 15,381.4 kg per hour of ethylene glycol and also 114,479.52 kg per hour of H2O. Next, we will move to the heat integration of our process plant. This is the stream data that have been extracted from our process. We have 2 cold streams and also 5 hot streams. This data later on will be inputted in the HIN software, and the software will do the pinch analysis for us, and this will be generated from the software. So from here we have the heating duties, which is 1,243.4 kilowatt, and also the cooling duties, which is 120,280 kilowatt. We also can get the pinch temperature from the software, which is 190 K. So from this information, we can use it to design our heat exchanger network. So this is the finalized design of our heat exchanger network. We can see from this design, we only have stream 2, only stream 2 and stream 3 is feasible to be exchanged. The rest, we have to install the heater and cooler. So from this heat integration, we can reduce the utilities, the hot utilities, up to almost 96%. We can also reduce the cold utilities up to almost 20%. By decreasing utilities in our process, we can also decrease the operating costs. This network design using pinch analysis will lead to maximum energy recovery in this process plant. So all energy is utilized effectively in our process plant.
Economy analysis is analysis that must be done for each plant design. This is where we need to evaluate whether our plant design is profitable or not, because that will be one of the objective of our plant design. A simple formula we will use is we will see whether our economic potential is having a negative or a positive value. If we are having a positive value, it means that our project is feasible to be done. And if we have a negative value, it means that our project is not feasible to be done. So let's see for our economic potential 1. So economic potential 1 will cover the total cost of product and also the total cost of feed. To be able to have a positive number of economic potential 1, your cost of product must be higher compared to your total cost of feed. This is where we will see that our plant design is profitable. Based on our literature review and research on the current unit price, we can say that the total cost of feed is 291,250,000 ringgit Malaysia, and the total cost of product for the terephthalic acid and the ethylene glycol is 332,489,571.70 cents. So to be able to have a economic potential 1, we will have the product, the total cost product, minus with the total cost of feed. Therefore, we will have a positive number of economic potential 1, 41,239,571.70 cents. So this shows that our plant design project is feasible. So to have a better understanding on economic analysis, we have also the economic potential number 2, where it considers the revenue, the total cost, and the total cost as well as the total utilities. Okay, in this matter, what we need to do is we will have the revenue, we minus with the total cost as well as the total utilities. In this case, our utilities, we only consider electricity, and the economic potential is in positive value, where we gain 31,944,266 ringgit Malaysia. And this had shown that our plant design project is feasible to be done.
Next, I will be presenting on the process flow diagram for our plant design project. First, I will show you PFD before heat integration. The PFD before heat integration starts with the daily PET flow rate for the plant, which is 59,523.81 kg per hour, which first is received by the PET grinder. In the grinder, the PET scraps are grinded into smaller particles of PET to ease the pumping process of PET into the depolymerization reactor R101. The grinder PET is pumped into the reactor through pump P101 at 2000 kPa into the reactor feed stream. In the reactor, the PET is reacted with ammonium hydroxide received from ammonium hydroxide tank T103, and the reaction are operated at temperature of 200 degrees Celsius and pressure of 2000 kPa. Before the ammonium hydroxide enters the depolymerization reactor, the concentration is maintained at 25 to 35 weight% of ammonia, temperature at 150 degrees Celsius, and then are pumped via pump P102 at 2000 kPa. The products of the reaction are diammonium terephthalate, ethylene glycol, and water. These products are then received by the filter S101, where the solid unreacted PET is filtered and are sent back for depolymerization reaction via stream 7, while the mixture of diammonium terephthalate, ethylene glycol, and water produced from the depolymerization reaction are received by the crystallizer A102 for further separation. Before entering the crystallizer, the mixture is cooled down to temperature 140 degrees Celsius by cooler E101. Moving on to the second section, which is solidification of TPA unit. It starts with crystallization of products from the filter S101, which is diammonium terephthalate, ethylene glycol, and water. The crystallizer is operated at temperature of 140 degrees Celsius and pressure at 250 kPa to produce slurry of diammonium terephthalate and ammonia, ethylene glycol, and water mixture. The mixture is then sent to the next unit, which is the ammonia stripping unit, while the slurry of diammonium terephthalate is sent to the centrifuge for further TPA purification. In the centrifuge, the liquid content in the slurry diammonium terephthalate is reduced to produce, and the liquid is recycled back in the crystallizer through stream 11. Then the centrifuge slurry diammonium terephthalate is sent to the Kern reactor, where solid terephthalic acid is obtained. The Kern reactor is operated at temperature of 275 degrees Celsius and pressure of 250 kPa, with the steam supplied to the reactor at a flow rate of 57,635.68 kg per hour. Ammonium hydroxide after the reactor is recycled back to the crystallizer via stream 17 after condensed via condenser E106 and cooled via cooler E103, while the solid terephthalic acid produced is sent to storage tank via stream 14. Moving on to the third unit, which is ammonium hydroxide recovery unit. It starts with the mixer tank M101, where the ammonia, ethylene glycol, and water mixture received from previous unit is mixed with lime. The mixture is then sent to the ammonia stripping column C101 via pump P103 at 130 kPa and control temperature at 50 degrees Celsius via cooler E102. In this ammonia stripping column, ammonia, ethylene glycol, and water is stripped by steam introduced at the flow rate of 247,354 kg per hour at stream 24 to produce ammonia hydroxide as the top product and ethylene water mixture as the bottom product. The outlet of the top product from the ammonia stripper is then condensed through the condenser E105 and cooled to temperature 25 through E104 before sent to the ammonium hydroxide tank of T103. Now, moving on to the ethylene glycol distillation unit. Ethylene glycol unit starts with the ethylene glycol and water mixture introduced to the distillation column C102 at the temperature of 107.35 degrees Celsius and pressure of 130 kPa. The ethylene glycol and water mixture is then separated in the distillation column C102, where wastewater is produced as a top product and from distillation, and ethylene glycol as the bottom product. So the outlet of the bottom product from distillation is then cooled to temperature 25 degrees Celsius through E107 before sending to the ethylene glycol storage tank T101 via stream 32.
Next, we will move to the heat integration of our process plant. This is the stream data that have been extracted from our process. We have 2 cold streams and also 5 hot streams. This data later on will be inputted in the HIN software, and the software will do the pH analysis for us, and this will be generated from the software. So from here we have the heating duties, which is 1243.4 kilowatt, and also the cooling duties, which is 120,280 kilowatt. We also can get the pH temperature from the software, which is 190 K. So from this information, we can use it to design our heat exchanger network. So this is the finalized design of our heat exchanger network. We can see from this design, we only have stream 2, only stream 2 and stream 3 is feasible to be exchanged. The rest, we have to install the heater and cooler. So from this heat integration, we can reduce the utilities, the hot utilities, up to almost 96%. We can also reduce the cold utilities up to almost 20%. By decreasing utilities in our process, we can also decrease the operating costs. This network design using pH analysis will lead to maximum energy recovery in this process plant. So all energy is utilized effectively in our process plant.
Next, I will present on process control and piping and instrumentation diagram for our plant design project. This is the complete P&ID, and it can be divided into 4 parts, which are basically process control in depolymerization reactor, process control from crystallizer until storage tank, process control from mixer to the ammonia stripper and ammonium hydroxide tank, and process control from distillation column until ethylene glycol storage tank. So the first part is process control in depolymerization reactor. First of all, we control the PET inlet flow rate into the grinder by using feedback control. Next, we control the grinder PET flow rate outlet flow rate from the grinder by using also feedback control. Next, we also control the grinder PET inlet flow rate into depolymerization reactor by using another feedback control. Furthermore, temperature of depolymerization reactor, which include the inlet of ammonium hydroxide into the reactor, is also controlled by feedback types of control. Furthermore, pressure inlet of ammonium hydroxide into depolymerization reactor is also controlled through a feedback control system. Next, the solid unreacted PET flow rate at stream 7 is controlled by a feed-forward control system. Moving on to the second part, which is process control from crystallizer until the storage tank. The feed temperature into the crystallizer is controlled through a feedback control system, and the flow rate of the feed into the crystallizer also feedback control system, whereas the pressure of crystallizer, which is the top outlet flow rate, is controlled by feedback control system, and the temperature of the current, which regarding the flow rate of the steam into the current, is controlled by a feedback control system. Furthermore, the inlet flow of produced TPA into the TPA storage tank is controlled to feedback control system, and the flow level of storage in the TPA storage tank, feedback control system, and the inlet flow rate to condenser E106 as shown in the P&ID diagram is also controlled to a feed-forward system. And lastly, the inlet flow rate to crystallizer from the condenser is also controlled through a feedback control system. The third one is process control from mixer to the ammonia stripper and ammonium hydroxide tank. First of all, the temperature of mixture in the mixer tank is controlled by a feedback control system, and the inlet flow rate of lime into the mixer tank is also controlled by a feedback control system. Moving on, the feed inlet flow rate of ammonia into the ammonia stripper C101 employs a feedback control system, whereas the inlet flow rate of the steam into the ammonia stripper, which uses a temperature transmitter, also employs a feedback control system. The pressure employs a feedback control system, which measures and manipulates the top outlet flow rate of ammonia stripper. Furthermore, we also control the outlet mixture temperature of cooler E104 through a feedback control system, and the ammonium hydroxide level in the ammonium hydroxide storage tank by manipulating inlet flow rate of ammonium hydroxide into ammonium hydroxide tank T103 is also controlled through a feedback control system. The last section, which is process control from distillation column until ethylene glycol storage tank. The flow rate inlet to the distillation column is controlled by manipulating the flow rate inlet to distillation column at stream 26, which is using a feedback control system. Moving on, the pressure of distillation column by manipulating the vapor outlet flow rate of distillation column is controlled through another feedback control system. Subsequently, the temperature of distillation column is controlled by manipulating the temperature of mixture recycled back to distillation column C101 after the reboiler, which is also a feedback control system. Next, moving on to the storage tank section, the temperature of the mixture is controlled by feedback control system, and the level of e.g. liquid in the storage tank, we also employ a feedback control system in order to measure the accurate liquid level at any particular time in the storage tank.
Now, we are going to move on to the next topic, which is HAZOP. So, HAZOP is one of the techniques used in evaluating the process hazard with the aim of identifying potential hazards in the process. So, from HAZOP, we can identify the possible cause and consequences based on deviation of parameter using guidewords, and then recommendations are added in order to strengthen the safety if the existing safeguards are unable to handle the deviation. So, this is a step-by-step procedure on how to conduct HAZOP, first with node selections, and then with the design intention descriptions, and identify the cause of deviation and consequences, and listing down the existing safeguards, and recommendations are added in order to improve the safety. And then we conduct this until the last guidewords and proceed with the next nodes until all nodes are evaluated. So here is the nodes identified in our PNID. There are 3 nodes identified. The pink one is node 1, the blue light one is node 2, and the blue one is node 3. And then I'm going to discuss in detail for node 1 only for our presentations. So node 1 of our process is from feed PET to heat exchanger E101 through depolymerization reactor R101 and filter S101. It also from pump P102 to depolymerization reactor R101. So the design intent is to depolymerize the PET into diammonium terephthalate and ethylene glycol solution mixture. So here there are 3 parameters, which is first flow, pressure, and temperature. So the guide used for flow is no less and more. So for deviation no flow, the possible causes is first blockage of valve V0102 and valve V0102 rupture. And the consequences can lead to no feed flow to reactor, causing failure of production. So the existing safeguards is control valve CV0101, and the action recommended is to perform regular checkup and maintenance on valve V0102 and control valve CV0101. And since there are no alarm there, we recommend to install flow alarm at stream 1. And for less flow, also possible cause is pump malfunction, and then thus leading to less feed rate to the reactor, and also low flow rate of ammonium hydroxide. And the existing safeguard is CV0103 and FV0304. And also the action recommended is to perform regular checkup on the pumps and to install flow alarm at stream 3 and 30. And for more flow, also for because of pump malfunction and high recycled stream 7 flow rate. And also this will lead to high feed flow rate into the reactor, thus increasing the reactor pressure. And the existing safeguard is CV0103, FV0304, and FV0104. And the action recommend can be referred to less flow action and to install flow alarm at stream 7. And for pressure, we have 2 deviation, which is less and more. And this is the cause can be because of pump malfunction, thus causing less feed rate to the reactor. And the safeguard available is CV0103 and FV0304. And the action suggested can be referred in less flow action, and to install pressure alarm at stream 3 and 30. And for more pressure also can be caused by the pump malfunction, thus causing more feed rate into the reactor. And the safeguard available is CV0103 and FV0304. And the action is the same in less pressure action, and to install relief valve at the reactor. And for temperature, there are 2 deviations, which is first less temperature and more temperature. And this can happen because of heater F101 malfunction. And this causes to low heat supply to the reactor for less temperature and high heat supply for more temperature. And the existing safeguard there is TIC0101. And for less temperature, we recommend to install a temperature alarm at stream 34 and regular checkup and maintenance on the heater. And also the action recommend is the same for more temperature. So now we are going to move to plan layout. So here is the plan layout of our plant. It is divided into 2 sections, which is first production area and the second one is non-production area. And listed on the slide is the area included in non-production area. And here is the units in the production area. Mostly it includes the main process units in our plant, and also the plant control room. So that's all. Thank you.